Good morning, everyone. I hope you are enjoying this session today. I'm Mustapha Hamad. I'm a PhD student. Today I'm halfway, let's say. I'm defending my midterm. And also I'm presenting joint work with Professor Michel Wigger and Professor Mireille Sarkis about multi-sensor detection under variable length coding. So first, who never heard of Internet of Things here? You can raise your hand. Well, I guess everyone heard of Internet of Things. It is very popular now, and the future Internet of Things is very promising, and we can see it applied in each and every area. For example, especially in distributed monitoring and alert systems, such as health monitoring systems and security systems. And even more precisely in the security systems, we can do systems that can detect a cyber attack or it can detect a fire incident, for example, or even a building security breach. I will just stop my video. I think the quality is being affected. Sorry for that. Now, is it better? Is the sound clear?
More or less. It's okay, go.
Okay, thank you very much. Okay, so in such systems, we can observe that we have many sensors. These sensors have to collect data, and they have to share this data with the decision center. And by decision center, we mean, for example, a one node that can receive all this information or a compressed version of this information that the data being collected, and then it will have to take a decision whether we are in a normal scenario or a suspicious scenario. We illustrate on this later on. But in such systems, the communication that happens between the sensors and the decision center, and even between the sensors themselves, is restricted with low delay communication. This means, for example, in a health monitoring system, we cannot afford even milliseconds of delay in taking a decision. And the delay in communication will be very dangerous in such a case. Even more, these nodes, all of the nodes, share the network resources because we cannot allocate in these days like dedicated network resources for each node in the system, for each sensor, for each even decision center. At the end, if we have communication, we have to share the network resources that we have. So let's take a very trending example. It's about COVID-19. And we assume here we have a patient in ICU. So we will have many sensors in the room that are measuring some parameters. For example, the movement, for example, also the oxygen level, detecting something that is expected to happen in an ICU unit. And on the other side, we'll have a patient, and this patient will be connected to some devices. These devices will have local measurements, for example, for his heart pulse rate, for his breathing activity, etc. And the goal of such connected system is to test if there's something suspicious happening. If there's, for example, severe symptom. So, for example, in COVID, we were surprised when we hear that there is loss of speech or movement symptom with the COVID. This was not really normal symptom. And in such cases, if we can see that the measurements between the sensors and the decision center, I mean here the local measurements, are really correlated, meaning they are as expected, they are as the statistics show, then we are in a normal behavior. However, if these measurements are independent, then there's something suspicious happening and we have to raise an alert. The goal in such a system is to guess correctly the joint distribution behind underlying these observations. So let's go deeply into the system model. In fact, as we can see in such a cooperative map, it's the main system model that we work on. We have two nodes, TX1 and TX2. These represent the sensors, for example, in the room. And on the other side, we have RY representing the decision center, and which has its own local observations called YN here. So what happens first So what happens first is that this system has to detect which hypothesis are we under. It means, are we under the normal behavior, we call it null hypothesis, or are we under a hazardous case, which we call it alternative hypothesis. This scenario is called in the literature testing against independence, and it is for binary distributed hypothesis testing. And as we can see for testing against independence, under the alternative hypothesis, as we said earlier, the observations are independent of each other. Okay, so what's happened in detail is that first, TX1 is observing the source sequence X1N, and thus it computes its message M1 in terms of this observation, and it sends this message M1 to both the receiver and to the other transmitter. And this link is usually called cooperative link. Why? Because at its side, the second transmitter, TX2, will now see the message that came from the first transmitter, M1, and it, using its own observation X2N, it will compute the message M2. This means that using the help of the first transmitter, the second transmitter can send improved information or message to the receiver ROI. And now the receiver ROI, using both messages and using its own local observation that was directly connected to it, for example, the local observations in the COVID example, heart pulse rate, oxygen of the lungs, etc. And using all of this information, it will determine if we are, or let's say it will guess if we are under the null hypothesis or the alternative hypothesis. And this is a single bit decision, which is equal to 0 or 1. Here, we consider in our work a Markov chain called X1N, X2N, Yn. The intuition behind this Markov chain is that sometimes these distances are not really equal, and maybe the second node will be nearer to the decision center, to the receiver, than the first node. And if in such scenario, the observations at Yn depend, given X1N and X2N depends only on X2N, we call this a Markov chain. And in such scenario, we can see that the probability distribution for the three random variables, x1, x2, y, will be given as px1, x2 times py given x2 only, and not py given x1, x2. So before going into the results, we have also to see some practical intuition behind our work. So actually, we have two constraints to consider: either the maximum rate constraints or the average rate constraints. And what is the main difference? In the maximum rate constraint, the length of these transmitted messages is usually upper bounded by a maximum constraint. So the allowed rate will be the maximum limit of this length of the message. So actually, we don't have flexibility in choosing our messages length. We have to be restricted by one maximum constraint. And in such scenarios, the fixed length coding is optimal, meaning that we can just use a fixed length for the messages, and they can be equal messages, for example. However, in an average rate constraint, we are concerned with the expected length of the message. And this gives us more flexibility. We can sometimes go beyond, and sometimes we can go below. The important thing is to conserve our expected or our average length of the message to be below the allowed constraint. And here by allowed constraint, we mean that like the available rate in the system, which is the network resources. In such scenarios, variable length coding, as we show later in this presentation, can definitely induce some gains. So what happens here? Like, what is the goal of this problem? Our goal actually depends on the type of errors that we are considering. So when we decide, we have two types of errors to consider. First, we have the type 1 error, and this is usually meant by false alarm or false positive. And it means that we will say that we are under the alternative hypothesis, which is the more dangerous one, which is the hazardous one, given that, in fact, everything is normal, and the true hypothesis is just h equals 0. However, for the type 2 error probability, and it corresponds to the misdetection, which is more serious, it means that we say everything is normal, the patient is under normal symptoms, and then suddenly we see that the fact is that the correct distribution or the correct hypothesis is h equal 1, the alternative, and what's happening is something dangerous. And such misdetection, especially in medical or security systems, is very important to decay to zero as fast as possible. We want this type of probability to be zero as n tends to infinity as fast as possible. And what we have to respect or to keep in mind that we have to remain under a type 1 error probability threshold. This means that epsilon here being the threshold of the type 1 error is the allowed percentage of false alarms. For example, if epsilon was 0.1, then we can have 10% of the time having false alarms. It's better than having, for example, high number of misdetections. But how can we understand this more related to our work? In fact, as you can see here, we define an error exponent. The error exponent actually is the slope of the decay to zero here as n tends to infinity. So we call an error exponent theta greater than zero as epsilon achievable if the following constraints are satisfied. And also here we can see that the error exponent is determined by the block length as it tends to infinity. And then the optimal error exponent is usually the maximum among all these achievable exponents. So take care when you are deciding in terms of null hypothesis or alternative hypothesis. Before going to our results, we present some related works. Actually, there are many works in the distributed hypothesis testing scenarios, and recently it's gaining more attention due to the future Internet of Things. There is many setups also, like not only just point-to-point or cooperative map. There is also the interactive. There is also when we have multiple decision centers. If we have cascaded setups, we will not go into all these details, but we will explain just the basic one. So for the point-to-point setup, Han was able to for sure under fixed length coding, was able to give a very practical scheme. In fact, when we have observation of xn here we have only one node tx as transmitter and only one node ry as receiver. If tx is observing the source sequence xn, then this scheme tries to quantize xn to un of m. And here the small m is the index, is an index going from 1 to 2 power n r that respects the length of the message constraint. And if we can find such a choice of m that tells us that the type of these sequences unm and xn are according to the probability of pux, meaning that we have something expected according to the statistics and related to each other, then we just send this index that we found to that like a compressed or quantized version of the source sequence xn. Otherwise, if we have like strange input, like a strange sequence that we are observing, then all what we have to do that tell them, we give up, let's send m equal to 0, which will tell the receiver, just raise an alarm. So now at the receiver side, if m is greater than or equal to 1, meaning it's not 0, or we can choose any other value indicating that it's strange, then it will check also if this received un of m, capital M here, and its local observation yn are also, the type of them is according to the probability distribution PY, meaning that it's also normal to have it, it's expected. Then we say, okay, everything is normal, we are under the null hypothesis. Otherwise, we raise an alarm and we say that we are under the alternative hypothesis. So mainly, we now present like what recently, sorry, before going to that, under fixed length coding also Al-Swedi and Shiger were able to determine the optimal error exponent for testing against independence. In fact, here we can see that their theorem holds for epsilon, for all epsilon greater than 0. This means that they have a strong converse, that the optimal error exponent here is independent of epsilon. And this is important to keep it in mind for later to understand what's happening exactly. So what happens under variable length coding? Well, Saclay and Wigger were able recently to apply variable length coding to the Swedish user setup. And what happens actually is that when they look into all the alphabet of the XN observation, we try to choose any subset called Sn with the probability that the observation Xn lying in it is equal to epsilon. And then if we are in this set, we say, okay, we can bear epsilon percentage of type 1 error. So why we just send the alternate, like a message telling the receiver to say, okay, now you can raise an alarm, whatever the real hypothesis is. This means that we can get benefit of the allowed type 1 error probability in order to reduce or to speed the decay of the type 2 error probability to 0. So now if X, the observed sequence Xn, lies in the set Sn, we will just send a single bit m equals 0, and then when the receiver receives this message, it will decide that we are under the alternative hypothesis. In such scenarios, type 1 error probability, yes, is upper bounded by 1, which is not actually the allowed threshold, but let's remember that this is happening only with the probability epsilon. And on average, we will have for this case only an epsilon upper bound. And the type 2 error is just 0 because we are always deciding in terms of the alternative hypothesis. And approximately the rate here is 0 because we are only sending 1 bit in terms of n, which tends to infinity. However, if we are not in this set that we chose arbitrarily, then our scheme would, the scheme of Saclay and Wigger just coincide with the fixed length scheme of Swedish, and thus we can choose the type 1, we can get a type 1 error equal to 0 by just choosing epsilon equal to 0. Because remember, the result applies for all epsilon, so it doesn't matter what epsilon we take. And the type 2 error now is upper bounded, and we can see here, this is the error exponent, because as n tends to infinity, this will be the optimal error exponent. And here the rate, as in the Swedish user case, is upper bounded, lower bounded by the mutual information between u and x. And thus, we can see on average, we can, because this is only for 1 minus epsilon of the time, and the other epsilon is just equal to 0, rate, we can see here we gain in terms of the rate. So the important observation by Saclay and Wigger is that the optimal error exponent under variable length coding is equal to the optimal error exponent under fixed length coding, but with R being boosted. So it's like for having for having smaller rates, we can still get the same value. So now for our setup, the cooperative map. The main result that we have here is in two things. First, we extend the achievability scheme that we presented now for the point-to-point under variable length. And the second thing, we have a converse also for our result. But let's explain first the achievability scheme. So the main trick here is that we are still defining the set as earlier. But now when we are lying in X1n being in Sn, then we will just send the message M1 equal to 0 also to the second transmitter, telling them to send the message M2 also equal to 0. And now both links, both rates are sending only just 1 bit, meaning their rates are standing as approximately equal to 0. And again, you are raising alarm under this scenario. However, if we are not in this case, our scheme coincides with the fixed length scheme of the cooperative MAC. In fact, Zo and Lei were able to provide a weak converse, which means it holds only if epsilon tends to 0, a weak converse result for the optimal error exponent under cooperative MAC. However, they have they had an error in their converse proof. We fix it, and we also present a strong converse in the next slide. So in this result, the optimal exponent will be the mutual information between U1, U2, and Y. And these are the rate constraints that to be respected. We can see here our theorem. It's for sure under the Markov chain X1 and X2 and Yn. But however, we have to note that the achievability holds with or without the Markov chain. But for the converse, which we don't present here because it's more technical and it will get you bored, honestly. So we have it only under the Markov chain x1 and x2 and yn. So you can see in comparison with the fixed length result, that also it's our result, the strong converse, the rates here. So we still have the same optimal error exponent, the same conditions to be respected for choosing the auxiliary random variables u1 and u2. But the main difference is in the rates. So here we don't have the 1 minus epsilon factor. This means this is under the fixed length. This means that the variable length coding is able to boost all the rates in the system by by the factor 1 over 1 minus epsilon, as we can see here. We also support our results by a numerical one. In this simulation, we consider actually an example for x1 and st being IID according to Brunello distribution. These are the parameters that we take. And it looks like the SBS, the doubly symmetric binary source channel. But here we are concerned with the maximum rate constraint, meaning that both rates R1 and R2 should be upper bounded by R that we vary here. So now, as we can see in this plot, the optimal error exponent for variable length coding is in red, and it is actually giving us gain over the optimal error exponent for fixed length coding, and both for the cooperative map in blue, dotted blue. So actually, as we said theoretically, that the optimal error exponent for 1 minus epsilon R, meaning here, if you, for example, if we choose any R, for example, R equal to 0.6, then almost 1 minus epsilon will be here for epsilon equals 0.07. We can see that it is equal, if we take a small shift here, to the error exponent at greater rate for the fixed length, which is this we call the 1 minus epsilon factor gain. And as we can see also, as the rate increases, here we tend to an optimal exponent for the central hypothesis testing. What do we mean by central hypothesis testing? It's actually when the decision center can have direct observations to all the sequences x1n, x2n, and yn. There's no need to compress, no need to communicate anything. It's like having infinity of bits sending. So this was for the cooperative MAC. Now for the non-cooperative MAC, the main difference is in the absence of this cooperation link. So actually the sensors are not communicating with each other. And the main difference now, the message M1 and M2 will be based on each sensor observation, X1N and X2N. And briefly here, our theorem shows that under the non-cooperative MAC, we cannot gain the same gain as in the cooperative MAC. We can see here the rates are boosted by 1 minus epsilon 1 and 1 minus epsilon 2, where epsilon 1 and epsilon 2 both upper bounded by epsilon, and they are subject to this constraint. What does this constraint actually mean? Okay, it means that if we, now you see it here, if we can have two subsets, Sn and Tn of the alphabet x1n and x2n, with the probabilities equal to epsilon 1 and epsilon 2, respectively, then now we want, like, whenever we fall in this or in this set, to send just one bit telling the decision center to declare h hat equal 1. But the problem here, as you can see, that we have to take into consideration the type 1 error. So ideally, we would have here probability epsilon and here probability epsilon. And then whenever we fall in one of these two sets, we will just send a 0 bit. And then we can get the same gain as in the cooperative MAC. But we have to take into consideration that the union probability of being in this set and in this set is equal to being in Sn plus being in Tn minus being jointly in both of them. And the joint probability that we call A here, if it is like not 0, then we are not respecting the type 1 error constraint that alpha n should be an average less than or equal to epsilon. So in this achievability scheme, the only case where we coincide with the fixed length scheme is if x1n is not in Sn and x2n is not in Tn. The important thing also to note here is our intuition that if we choose Tn, the second set, to be an empty set for the cooperative map for the same coding scheme, and if x1n lies in Sn, we just transmit a single bit message as we explained earlier, then for the same coding scheme, we can get for the cooperative map the full gain, the 1/1 minus epsilon gain, for all links simultaneously. This shows that the same coding scheme now is more beneficial for the cooperative MAG, and meaning that in the variable length coding scenario, and meaning that the cooperation is very important in the variable length. It adds more benefit than just in the fixed length one. However, we have a remark for a special case for the non-cooperative MAG. If we can find epsilon1 equal epsilon2 and the joint probability A equal epsilon, then we can show that we can still get the full gain, but this is only in special cases, such as is the probability distribution between Px1 and x2 is like deterministic, and this is not always the case. Also, we can prove an upper bound, saying that the best thing that the non-cooperative MAC can show is that it can do as good as the cooperative MAC. However, this is not a tight converse because the achievability cannot achieve this result. And this means that a tight converse is still open for this problem. The last setup that we present quickly here is the interactive communication. We also worked on it, also for sure under the average rate constraint, the variable length coding. And we can say that here we can easily extend the 1/1 minus epsilon communication gain that we observed earlier with the cooperative MAC and the point-to-point setup to the two-round interactive setup. In fact, we cannot, however, prove that this is the tight converse or this is the best result that we can achieve, meaning that a better achievability scheme could also be possible, and it stays an open problem. Finally, so as we presented earlier, the three main setups that we worked on, the cooperative MAC, non-cooperative MAC, and the interactive communication, we are interested in the future also to consider the cascaded setup. Actually, this setup is interesting because it looks like the cooperative MAC. However, the link between Tx1 and Ry does not exist here because the distance might be very large, and such a link might be not feasible, not just like we considered in the cooperative MAC under the Markov chain. And for such a problem and testing against independence, but with two decision nodes, for example, like this relay also takes a decision, Salah, Kalibar, Uyghur, and Wang were able to prove a weak converse result for optimality. And also Sao, Zhu, and Tan were able later to prove that the result also can be supported by a strong converse, which holds for all epsilon. So our first step was like simplifying this strong converse using our technique for the converse. Our converse was, let's say, complicated and hard, but it's still simpler than much simpler than their converse. Also, we look into having optimal results for the scenarios in the variable length coding. And for the cooperative MAC setup, we are interested in studying when we have different sources. For example, if the message from the transmitter Tx1 to the transmitter Tx2 is different from the one sent to the receiver. If we have different encoding functions, different rate constraints also, and to consider also the total compression case. Maybe if we have only one bit being transmitted from Tx1 to Tx2, for example, on the cooperative link, and for sure to study more practical scenarios, let's say, with finite block lengths, because all of our work is as n tends to infinity, infinite block length. And we are already working on a practical implementation at Cortex Lab in Selenium. And finally, here are my references. And thank you very much for listening. Please let me know if you have any questions.
Yes, thank you, Mustapha, for this nice presentation. Maybe there is something I missed between the comparison from cooperative to non-cooperative MAC. So it was in slide 13 to 14. So maybe can you comment once again the difference in terms of error exponent between cooperative and non-cooperative MAC.
Yes, definitely.
What are your conclusions?
Yes, definitely. Thank you very much for your question. Actually, the main difference is that for the cooperative MAC and the achievability scheme, as we saw, when I have just one, okay, one more. Yeah. Whenever we fall in this set, both links can send the 0-bit, and so both links can reduce their rate by the factor 1 minus epsilon, because this set is only for epsilon of the time. So this means that we can boost all the rates by 1 minus epsilon factor. However, for the non-cooperative MAC, we cannot know, like there is no shared information between the two transmitters. So we cannot know if one of them is in the set that we chose for it, meaning that if, like for example, here if we fall in this set and this set like not in the same time, so for example they are totally independent, it means that if we choose the probability to be epsilon and reduce the rate for epsilon of the time, then we will exceed the allowed threshold for the type 1 error probability overall. So we can get only 1 minus epsilon 1 and 1 minus epsilon 2 gain, 1 minus epsilon 1 for the first link and 1 minus epsilon 2 for the second link, where epsilon 1 is less than or equal to epsilon and epsilon 2 is less than or equal to epsilon 2. So it's like less gain here for that length coding. Is it clear now?
Yes, it's quite clear.
When you have a Markov chain, why is the message sent by X1 useful? Why does it bring some information? Could you give some insight about that? Why isn't X2 sufficient from the second transmitter?
Actually, this is a very good question. I also asked to myself earlier. In fact, sometimes there is a, let's say there is, because we can see that there is a cooperative link between X1 and X2, right? Good. So the idea is that sometimes you can see some information at the X1 side that because we have correlation between X1 and X2, X1, X2 are not independent. So this can let the second transmitter to send another information. So if we just send, if we just depend on the, if we don't have this link, okay, then we lose some information. Why? Because the second transmitter now like have to send all the information depending on what he received from the first transmitter. The first transmitter, when he sent the same information that was sent to the second transmitter, he is like now helping the second transmitter to send less information to the receiver. So this can be like part of the information, and this is the other part. However, if this link doesn't exist, even if X1 helps X2N, and X2N knows what to send to the receiver, it has also sometimes to consider what was sent by X1N and send part of it in this message to the receiver, because now the receiver doesn't know anything about what was happening. The more important, like the more value of this link can be seen when we have different source messages. That's why we consider this in the future work. So because if we have, for example, here another message, sometimes it's enough only to send 1 bit here, or we are constrained, let's say, by a low rate on this link. So this is what we have intuition that maybe even under this Markov chain, we will still have very, let's say, wide gain in having both links. And that's why we will compare like this setup with cascaded setup. Because the cascaded, for example, under the fixed length coding, with having only with having this Markov chain and with having only one decision node, tell us it's like just to how to say it, to ignore the message that was sent from N1.